Mabilis. Okay, so let's now talk on some terms used for the design of laterally supported beams. Um, for the beam classification, we take note that we have some classification according to the importance of the member, if it is a primary beam or a girder, or simply a secondary beam or a joist. Of course, when we talk of importance, the beam and the girders are more important than the secondary beams because they are loaded heavily and they are supporting more parts of the building. Okay, girders are simply large beams that supports maybe a major part of the frame, like beams. It can support beams. It can also support columns, no? So the transfer girders, yung mga planted columns, can be supported by large girders, no? For joists, this normally supports the floor, the walls, etc. Okay, so these are directly supporting the floor system. And for the lintels, these are supporting portions above an opening. Okay, so lintel beams normally supports loads above openings. Parlins, they are supporting what? Roof system. Okay, rafter also support the roof system, no? Or simply the parlins itself. Spandrel is a term that is being used differently by architects. No? These are normally those uh, portions of structures that are above arcs. Sa architectural yon, no? But for structural engineering, spandrels are simply your exterior beams are called spandrels because the exterior beams are the ones carrying the curtain walls, the exterior walls, which encloses your structure. So kaya tinawag silang spandrel, no? Just like a spandrel ceiling, it encloses the ceiling part, no? Pero dito we're talking of course of beams. Stringers are beams that are what connecting two other beams, like a stringer. If you have a main beam here and a beam there, you call this now stringer, or sometimes you call this the intermediate beams. Okay, a stair is a stringer that connects a floor to the other floor below or above it. Okay, so these are connecting beams. Okay, so the word laterally stable and unstable has something to do with the stability aspect of your frame system. Okay, so when you say your beam is laterally stable, does it mean that it is laterally supported or laterally braced? Okay, so when you say stability, it has something to do with the behavior, no, aspect. So when you use words in your thesis, you must be very careful in using these terms. Just like what I presented here, is laterally supported is the same as laterally braced. Their action is the same, but they are actually different. No? So support has something to do with the general description on how the edges of the beam is restrained from moving, while brace is a different thing. No, it has something to do with the framework itself. Okay, so this support is a condition, but this is something to do with the system or the frame. So do you support it? Do you brace it with another beam? You brace it with a lattice structure. You brace it with the so it depends on the type of frame system that you use. Okay, while support is more on a general term that gives you how it is braced. Is it braced continuously? Is it braced in a certain interval, and so on and so forth. Okay, supported and restrained are actually very close to each other. So when you say laterally restrained, so if you read the literatures and books, um, might as well look into how those words has been used. Okay, other slides here are discussed in our first few topics, like the allowable stress design. Okay, why is it called the permissible? I use a different reference here. I think this is an Indian reference. Okay, I downloaded this uh, from an Indian reference. So they are using the word permissible instead of allowable. So we have studied here limit state designs of beams, okay, which has something to do with the strength limit state and the serviceability limit state, and so on. Okay, so these are the strength or the ultimate limit state, serviceability. Loads are also defined. Okay, so I will no longer. So let's jump into stability of beams based on lateral support requirements. So again, when I say lateral support, this is a condition into which your edges are restrained from moving. Okay, so when you say a lateral support beams, you are actually referring to a continuously restrained beam at the edges. Okay, so if they are continuously restrained, then they are said to be laterally supported. When you are talking of lateral and supported, these are now the uh, braced, okay, laterally. Okay, so there are some beam, maybe it can be a secondary beam bracing, it can be a lattice bracing coming from uh, or connected from one beam element to the other beam element. Where do you connect it? Will you connect it at the flange, or will you connect it at the flange, bottom flange rather, or at the top flange, or at the web? So those are things that you need to to look into also, no? Paano mo siya i-connect. Okay, kung walang problema sa budget, i-connect mo lahat, no? Para nun, wala ka ng problema. But if you understand the theory, you have an idea on where to connect it. Prioritize, kung lalo na kung konti lang ang budget mo, baka pwedeng i-connect mo lang yung bottom flange o kaya yung top flange para nun mag-i siyang brace. Okay? So again, we are preventing here lateral torsional buckling. So a little bit of side and a little bit of twisting. So the definition for laterally supported is when a beam is subject to bending, there's a tendency for the top flange in compression to pull the section out of plane and cause buckling. In order to prevent this and allow the section to achieve its full moment capacity, it is important that the compression flange is restrained so that only vertical movement of the beam is allowed. So a continuously restrained or a restrained beam is called a laterally supported beam. And how do you make sure that it is continuously braced? So if you have here a wide flange section, where's the compression flange? Top or bottom? It depends upon the bending. No? So for positive bending, your top flange is in compression. And therefore, if I place a slab here, monolithically, not monolithically built, but it is firmly connected by some shear connectors on the flange, and this is a slab, okay, this is considered a continuously restrained condition, and therefore this beam is said to be laterally supported. Wala ka ng problema, no? Now, the conditions to qualify as a laterally supported beam may be put into detail, no? So it should not laterally buckle. Okay, so do you think this will still buckle if this is there's a slab restraining it from buckling? So I don't think so. None of its elements should buckle until a desired limit state is achieved. So it's also satisfied. The limit of state of serviceability must be satisfied. Of course, that will be kasama na yan, ano? Pati yung deflection mo is actually reduced when you're talking of deflection serviceability aspect. Members should behave in accordance with the expected performance of the system. Of course, that's the objective of making it laterally supported. And the lateral stability, in terms of putting a restraint condition, may be modeled by applying a support at the flanges. Okay, so para kang nag-apply na support dito sa flange, particularly in this case of continuous restraint. Okay, coming from the slab, the floor slab of the whole system. And if lateral stability is not achieved, this is a figure that shows you how it would laterally behave. Okay, so it will be displaced into a position laterally. At the same time, there's a little bit of twisting there, especially when the dead weight is imposed at the ends. Therefore, the lateral torsional behavior is emphasized at the ends. Okay, so this is just to exaggerate. Now, the question is, which is the better configuration as far as the axis of the beam is concerned? Is this the strong axis configuration or the weak axis configuration? So which is much far stronger against lateral torsional buckling? Ito ba o ito? Okay? So where are the compression flanges here? In fact, if you will look here in this orientation, you only have these tips, okay, that are placed into a extreme amount of compression, and of course tension yung other side, no? So you reduce the portion into which compression is being experienced by the section, and therefore this is a better orientation than this. But do you use this as a beam? Question, will you use this as your beam? Definitely that's not the basis upon which your beam shall be oriented, no, shall be placed. Because if you will be using this, then you have a very weak bending resistance. So this will give you a costlier design. Okay? That's why you go back to the strong axis uh, uh, configuration and put what you call the bracing system, so as not to allow your beam to experience excessive lateral torsional back. Pero in cases wherein there is no load class, ito napansin ko ito sa mga sa mga design ko sa roof, no? Steel roof framing system. Binabaligtad ko kung minsan ganito because of wind loads. Okay? Wind loads. Kaya nandito ako sa lateral ito. Binabaligtad ko, no? Nagtataka yung mga iba, ba't baligtad po yung ano nyo? Of course, you cannot explain much kung hindi naman technical yung kausap mo. So, you just smile and insist that they follow, no, your design. Okay, so this we discussed it already, but the terms were a little bit change, no, because this is an engine reference. So elastic, this is a yield elastic, this is a partially plastic, or what I call an elastoplastic, and this is the fully plastic. Okay, so they mean the same thing, but they are just presented differently. Okay, so how about the local buckling failure modes in compression? So, meron tayong tinatawag na, pasok na dyan yung local failure natin sa beams na to, no? Parang sa columns din, may local failure. At the same time, ito yung tinatawag nating flange buckling failure based on plate stability. Okay? So, yung dinerive natin nun sa plate stability, applicable pa rin dito yon, no? So, flange local buckling is unstiffened, no? Unstiffened buckling. Okay, so this is eventually based on the plate stability analysis that we have discussed on compression members. Because this is still compression, kaya lang, anong tawag dito, class? This is no longer uniform compression. Okay, so if we will look into our flexural diagram, yan, ganyan siya. Ang tawag dito is flexural compression. So pag tinignan mo sa table yan, sa code, flexural compression, hindi uniform, no? So pag tinignan mo ito sa taas, makikita mo, asan ba yung flange mo? Ito lang yung flange mo, no? This flange is actually a non-uniform compression. Okay? So iba yung limit dito, may adjustment na tayo dyan, no? Hindi na yung limit na ginamit natin sa uniform compression. Okay, for shear, failure modes in beams are actually described in this tension field action. Okay, so you call this the shear zone is actually a tension zone, no? Tension field. Shear stresses class are simply tension stresses, even in concrete. In fact, when we design shear, we call it diagonal tension in concrete. Tama? If you have the word diagonal tension, because we are expecting cracks to happen diagonally, in fact, the stirrups are much more efficient in concrete when you place them diagonally. Kaya lang walang gumagamit kasi mas madali nga naman pag diretsyo na lang. But kung kayong gagawa ng sarili nyong building class, no? Sa inyo yung building, kayo naman yung engineer, make it mas efficient pag in-inclined mo yung stirrup mo. Nasa code naman yung formula nun, kaya lang, madalang lang gumagamit kasi parehas din naman di ba? Mas madali, mas maganda, mas maraming kita pag madali. Okay, so these are called tension folds or tension buckling. So pag tension, ganyan yung designation natin, straight line. Kumisan nilalagyan na lang ng parang ano dito, ganun, no? Okay. But to indicate that may tension dito. Bakit tension? Kasi nakikita mo naman yung deformation niya humaba yung diagonal, kaya tension siya dito. No? So your force is actually pulling this in tension and this is pushing this in compression. Okay, so ganyan na dinidesign yung shear, tension pa rin siya. No? So kung makikita niyo yung formula natin sa shear later, it has something to do with the criterion for failure, yung pinakita ko sa inyo noon na von Mises criterion. Okay? So during the shearing process, if the web is too thin, it will fail by buckling or rippling in the shear zone as shown in the figure. But class, hindi critical sa tension ito, ano? Ang critical yung sa compression. Habang hinila mo to, kinompress mo yon, magkakaroon siya ng folds or simply buckle ang tawag, no? Okay, so other failure modes, ito yung sinasabi natin, yung ginagawa natin noon. Pag yung buong flange, buckling ang tawag. Pag kapiraso lang, crippling ang tawag, no? Pag nando lang sa bandang baba, normally, kung saan yung support, or nando sa taas, normally, kung saan yung concentrated load, crippling ang tawag, no? So, crippling is actually a small buckling. Buckling kasi is element failure siya kaya yung buo. Pag crashing naman, normally sa toe, no? Ito yung mga welded connection na mapapansin nyo pag rolled shape, walang problema sa crashing Kasi yan talagang ni-roll mo, may fillet pa siya. Pero yung mga nagmamarunong, naka-weld gano'n, nakaangat, tapos bibirahan lang nila ng makapal, pala mo totoo, pero nag-crash pala doon. Okay, so ingat kayo doon. Pag nag-deflect yan, maapektuhan na yung stability ng buong element mo, lalo na kung critical siya sa movement. No? Konting galaw lang, merong maapektuhan. Okay, so this is about web buckling and bearing failure. Okay, so ito yung lateral torsional buckling na sinasabi natin. Okay, so this is a simple plate element, buccal decompression. Kung diretso lang yung element mo, mapapansin mo class, yung top portion mo ng plate nag-bend laterally pero yung bottom hindi. Bakit hindi nag-bend yung bottom? Eh tension yan, hihilahin niya yung bottom mo eh. Kaya makikita mo dito yun lang sa taas ang nag-buckle. Eh dahil restrained siya sa support, hindi sasama yung baba at siya'y mag-twist. Kaya tinawag na lateral torsional buckling. Okay? Okay, so for other local buckling behavior of elements such as wide flange and a box element, so you will notice, maganda to pag ginamit mo ito sa mga modeling, 3D models ng mga software, pati yung stresses nila can actually be shown in terms of regions, no, of high stresses, contours, etc. No? Pwede mong i-model, mas appreciate mo yung drawing kesa dito lang. And these are now the comparison between a wide flange and a rectangular section wherein your K rectangular box section wherein your K value for the overhanging flange is 0.425 and this is 4.0. I think this is for simply supported both ends, no? So box ito, ano? And this is simply supported free. Okay, yung K natin, yun ang nagbibigay nung width to thickness limit mo on the basis of end conditions. So, which means that this is 8 times as strong. If you divide this, it's more than 8 times as strong than this one in terms of backleg. Okay? So, mas maganda pala ito na gawing beam o gawing column kesa dito. Ngayon, ang tanong na naman, alin ang mas matipid, mas mahal? Okay, kaya hindi ginagamit yung box. Diba? Kasi dito pa lang makikita mo na dalawa yung pinaka-web mo. Dalawa yung pinaka-web. Mas mahal ito. Diba? Okay, so still remember the formula we derived on the plate stability analysis. Ito yan, ano? Pag sinubstitute ko yung K doon, 16 ito. Okay? Itong 8 times as strong, considering K value pa lang yan, no? Pero ito, considering the buckling strength of your section. Okay, so remember that our formula for FCR on plate stability analysis is this one, no? So this is 12 K pi squared E over 12 times 1 minus nu Fy, walang Fy, B over T squared. Yan yung formula natin. Yung dinerive natin last time. If I substitute 36 KSI dito, kaya kumuha lang, E is 29,000. Ang makukuha mo is 16. So, pag nagtitingin ka na, pag basta flange ito, no? Sa flange, yung B over T mo, 2TF mo, dapat less than 16 siya, no? Para wala siyang buckle. Okay? Para mag-fall ka sa not slender, no? Hindi siya slender. So, at least tandaan niyo yung mga numbers na ito. Kahit nasa site lang kayo, nag-observe kayo, aba masyadong manipis yung ano mo, di ba? Hindi ba delikado mag-buckle yan? Okay. Tanungin mo na yung mga project engineer o kaya kung may mga design engineer doon, huwag mo tanungin yung foreman, hindi niya alam yan. No? Okay? So, mas mabilis, di ba? Okay, so this is a Indian standard, kaya IS siya, no? So I'm trying to read the now na medyo nagsawa na ako sa ano, mga standards. Pero syempre, iba na yung nakasanayan mo kung minsan eh. Naninibago ka pag ang maganda lang, you can compare it with matapang yung mga Indians kesa sa mga Amerikano. Something like that, no? So, alam mo rin yung history niya. So, yung mga gustong dito magpunta pag magtitesis, pwede rin, ano? Pero syempre, kailangan meron pa rin structural uh, touch yung ano mo, yung study mo. Okay, Stephen, pinag-usapan na natin to. So, I think we can just look into some of these sectional classification. Kaya ito yung ginagamit ko sa undergrad. I make sure naiintindihan nila ito. Okay, this is a moment curvature or rotation. Parehas lang sa moment na curvature. Ayan pa rin siya. So, kung mapapansin mo dito, yung curve natin, yung mga curves natin, kulay blue, green, ito, medyo blurred siya, tapos ano dito, yellow. So, it ranges from slender. Ano itong slender? Ito yung non-compact limits natin. Okay? Non-compact. Ito yung limit natin ng non-compact. Kaya kung natatandaan nyo yung pinag-aralan nyo nung college, non-compact tsaka compact section lang yan. Yung semi-compact, ito yung partially compact sa iba. Okay? So, itong compact, ito yung malapit ka sa plastic. Anong kaibahan ng compact sa plastic? MP lang yan eh. Parehas lang eh, di ba? Ang kaibahan nito class, this can give you rotational capacity. Sabihin, nag-rotate na siya ng malaki, buhay pa rin yung beam mo. So, sasabihin natin, malaki naman yung deflection. Oo, malaki. Anong nangyari? Lalong delikado yon. Hindi, kasi inabsorb mo yung energy. So, tandaan nyo, sa rotational capacity, energy absorption tayo. Ang earthquake class, wag mo labanan. Hindi mo tatalunin yan. Absorb mo yung energy niya. Parang meron ka ng damper dito na, kaya may damping ka eh, di ba? May natural damping ka. Kasi dito pa lang, makakakuha ka na ng ilang percent. Okay? Ductility-wise, okay din siya, di ba? Kaya, mas maganda pa rin, nandito ka sa banda dito. Ang compact naman, wala siya. No rotational. Merong konti. Okay. Ito large, ito small. So, pag ang ibig sabihin dito, hindi siya pwede mag-form ng plastic hinge. Dito ka lang pwedeng magkaroon ng okay? Ito yung mag-absorb ng energy mo eh. Yung plastic hinge formation. So, ano sasabihin iba, pagtapos naman ng earthquake, buhay pa ito, magre-retrofit ka na. Kung minsan kasi, ano yan eh, depende rin sa objective ng designer. Nakalagay naman sa code natin basta hindi bumagsak yung building natin, di ba? okay pa rin eh. And of course, tingnan mo sa cost. Kung konti lang yung cost na difference, ba't dito ka na lang? Pero talo ka naman sa energy absorption. Ano ibig ko sabihin doon? Kuwari, yung pumalo na earthquake sa'yo, hindi pangkaraniwan do sa expected mo, baka mas mabuhay ito kesa dito. Kasi dito, dahil wala siyang plastic hinge, hindi siya nag-absorb, nag-dissipate. Okay, another word is energy dissipation. Okay, ng energy, nilabanan niya, maaaring natanggal yung mga connections mo, pero dito hindi. Kasi napunta yung energy dun sa mismong plastic hinge, hindi naman dun sa connection. So look at things that way when you design class. Do not just memorize the procedure you see on books or taught to you by software technologies. Ang tawag ko pala mga sa software expert technologies sila eh. Ang galing talaga sila doon, no? Walang problema. Pero may times na pag wala silang, siyempre, titignan mo doon ano yung natapos nila. Hindi naman natin sila no? Minamata, pero they are dependent on what the software can offer. Tayo, ang advantage natin yan, pag natuto tayong mag-software, hindi na tayo kayang habulin. Imagine, yung driver mo is a professional race driver, may experience, tapos yung pinagamit mong kotse sa kanya is a powerful sports car. Hahabulin mo pa ba yun sa expressway? Huwag mo biruin yun. Hindi ka urungan, di ba? So, something like that. Yung software, yun yung kotse mo. Pero yung, yung experience mo and knowledge, yun yung master's degree mo. Yun yung knowledge mo dito. Okay, so, kaya ngayon, habang bata kayo, mas maganda, mauna muna yung knowledge bago yung, yung yung software. Pero kaya sabay, pwede magsabay, Ang nakakatakot lang nga kasi pag nauna yung software use, tatamarin ka na mag-aral eh. Galing mo na eh, di ba? Lalo na kung kumikita ka na ng malaki. Ba't ka pa mag-aaral? Sabi nga nila, if you can earn. Pero that's not the point of trying to earn a degree kasi, I know you know that. Okay? So, section classification now will be starting from plastic. Ayan, plastic hinge formation, compact, meron pa rin plastic resistance pero maliit lang yung plastic hinge rotation. Semi-compact, ito yung mga hindi yung may iwasan na syempre may part nung design natin na practically magse-semi-compact lang siya. At may part din na pwedeng pumunta sa slender yung section mo. Pero ako ayaw ko to class, no? Delikado to kasi konting pagkakamali mo. Be sure nandito ka sa tatlo. Sabihin na nilang takot ako pero napaka-brittle ng failure na ito. Kung meron tayong tinatawag na brittle failure sa steel, yan na yun. Okay, look at this. If you are designing a reservoir, ito yon. Ito yung pinakamagandang i-design mo. Diba? So, kung meron kang source ng tubig, nandito yung capacity mo. Imagine, di ka bumababa dito sa plastic capacity. Pag compact naman, pwede ka, parehas ka lang dito, pero wala kang binibigay na dinidissipate na energy. Parang tao ka na mayaman ka, pero hindi ka marunong mamigay. Pero yung yaman mo, pares din. Okay? Dito. Pero ito, kahit na gusto pa niyang yumaman, hanggang doon na lang siya. Na lang capacity niya. Okay, pag semi-compact naman, ang tinarget mo, yung yield lang. Dito ka lang. So, dito tapon ka na. At yung slender, hindi mo man ma-reach yung yield mo eh, no? May butas ka na doon pa lang in the midway, no? So tapon, hanggang dito ka lang. So nagtatapon ka ng resources, ng energy. Kaya this is tapos delikado ka pa na mawalan, 'di ba? Kasi yung capacity mo to give is napakababa. Okay. So these are just the comparison or the description of each and every behavior in terms of these figures. Okay, so again, this is an Indian code. Okay, so look at the criterion on the slender. Ayan, no, 16, no, yung kanina. Ito yung lambda R, no, 16 halos. So I think kalahati yung plastic. Oh. Pagdating doon sa flange criterion, unstiffened to, no? Sila hindi nila ginagamit yung unstiffened. Flange, ito yung unstiffened. Okay? Ito yung stiffened web. Okay, for the classification of Indian rolled shapes, yung sa American, mas mataas yung plastic eh. So pag nag-order ka ng mga rolled shapes sa American standard, I think most are hindi pala, mas maraming compact. If you look at these percentages, of course this is not percentage, no? Finite ano siya, value siya. Pero if you will compare to American standard, compare to Indian, I can roughly estimate that mas maraming compact sections sa mga rolled shapes ng American kesa sa Indian code. Especially yung Chinese, ha. So, yung pwede kayong mag-compare ng mga codes na ganun. Just for your reference. Maganda kasi alam mo eh, di ba? So, mas magandang pag-usapan mo pag ang kakwentuhan mo is not masyadong mathematical naman pag ang kwento mo sa kanila are the formulas. So, yan, yung mga practical ano na yan, maganda ring nire-research. Limit behavior of lateral restrained beam in its design. Okay, so ito yung pang ano na to. Pagkuha ng mga plastic, pinag-aralan na natin to. Okay, ito yung point. Tignan niyo yung point ng ano yan? Centroid nung tension area tsaka compression area. Okay, so it's almost at this transition. Okay? Kaya mamaya yung shape factor niya, makikita natin kung ano yung value. So this is the one that I'm talking about when I say laterally supported beam. Yan, meron siyang buhos, no? Yan yung laterally supported talaga class. If you will define a laterally supported beam categorically, technically, in terms of structural engineering, this is what a lateral supported beam is. Yung pag-aaralan natin, lateral unsupported are only braced beams yun. They are somehow stable in some conditions and sa iba hindi. Hindi siya stable. Okay, limit of laterally limit states. Okay? Of laterally supported beams or laterally strained. Yun yung counterpart ng word na supported, strained. Okay, if we look at the curvature of bending, yan na yan, no? So ito yung curve niya. Itong radius na to, ito yung rho natin, no? Curvature is actually the reciprocal of the radius of curvature defined in your structural mechanics, no? So pag binasa niyo yan sa mechanics of materials. Okay, ito na 'yon, no? So pag tinignan mo ito, dinerive mo yung flexural formula, 'di ba? Pag kinuha mo to tapos kinuha mo yung vertical, ito yung Okay, kinuha mo itong original sa vertical. Ito yung stress diagram mo. Okay? So, itong theta mo dito, ay yung phi mo dito, ito yung phi mo doon. Parehas lang yan. Okay? So, curvature and rotations are just the same. And they are just different on the amount of dx that you place to multiply it on the curvature to make it a dimensionless rotational parameter in radians. Okay, and that is the plastic hinge. Okay, ngayon, maraming nagtatanong, ano ba yung length ng plastic hinge? Pwede mong i-derive yun doon sa iyong equation. Di ba? Ako, yung confinement ko sa beams, when I say stirrups, hindi na ako nagdi-design ng stirrup sa shear. Kasi, kung minsan, maliit lang. I define the spacing of the stirrup at the plastic hinge region on the basis of moment curvature relationship. Kaya sinasabi ng iba, si engineer ang kapal ng stirrups. O, ngiti ka lang at alam mo naman na pag nagkataon, yung building mo matibay, no? So, tipirin mo doon sa pwedeng tipirin, doon sa nakikita mong wag dapat, ibigay mo talaga yung lakas niya, no? Sulit doon sa gastos nung may-ari. Okay, so this is an idealized elastoplastic. Diniscuss ko na kanina yan. No? So, inuulit ko lang itong slides. At ito naman yung representation ng moment curvature with respect to the deflections. No? So, habang nagiging plastic siya, ito yung slender, ito yung ito yung semi-compact, slender tsaka non-compact, pareho yun. No? So, yung semi-compact, ito yung compact, ito yung plastic. So, pansinin nyo, yung 1, 2, 3, 4, lumalaking rotation mo. Kaya dito, energy absorption ka na, energy dissipation ka na, no? Okay? So, yung energy dissipation is, can be shown by simply graphing the force deformation, no? If this is moment curvature or force deformation, okay, force, saan siya? Kuwari, force, deformation siya, delta. Parehas lang yan. Force times is work or energy, di ba? Okay, so pag meron kang malaking force, maliit na deformation, ang energy mo dyan is ito. Okay? So, pag binigyan mo siya ng, kuwari, nag-earthquake, may energy yung earthquake, no? Seismic energy. Pag binigyan mo siya agad ng malaking deformation, dito mo deformation, anong force ang a-absorb niya? Maliit na lang. Ito siya ngayon. So, pag akyat niya dyan, ay ito siya. Okay, so ito lang yung... Okay, yung area nito under this curve, pareho lang nung area nito, which is simply what? The energy, the seismic energy that it is going to absorb. So, yung force mo, yung base shear mo dito, or yung force na nandun sa internal force na inabsorb nung member mo or the moment absorbed is smaller than this force here. Or if you can get moment here, this is smaller than the moment here. Tama? So, pero yung energy inabsorb niya. So, which will you prefer? Okay? A bigger moment or a smaller moment? Okay, in terms of plastic na to, plastic, of course, you are talking of plastic. This is still elastic mode. Okay, so ganun yung energy natin. Ganun din dito. Ang ano lang ng mga ibang philosophies, sabi nila, after the earthquake, retrofit ka. Sila daw hindi. Okay, so may point din sila doon. But if you are talking of 100 years recurrence period, isipin mo naman yung 100 years mo. Sulit nang palitan yung building mo, di ba? Or 50 years recurrence. No, major earthquake na yan. Alam nyo class, yung 20 years na recurrence, like yung 1990 earthquake sa Luzon, ilan ng years ngayon yun? This is 31 years na yun, no? Hopefully, siguro sa prayers din, hindi pa dumadating yung susunod. Okay? Kung natakot ka do sa 1991, nag-design ka ng masyadong matibay na ine-expect mo na yung magnitude 9 na earthquake, talo ka na do sa investment mo, lalo na kung compare mo yung design ng WSD noon tsaka yung strength design ngayon, di ba? So, yun yung mga titignan mo dyan when you are trying to look into the Siyempre, ang tendency po pag lumindol, agad takot ka eh. Oy, titibayan ko na yung design. Pero tingnan mo naman yung recurrence. Buti nga, hindi pa nangyari yun. Sa Manila, mangyayari pa ba yun? May balita ba kayo doon sa Big One kung mangyayari pa yun? Okay, so ito yung plastic moment, yield moment na diniscuss ko a while ago. Kaya lang hindi natin pinakialaman yung strain hardening. Sa shape factor, ang pinaka-efficient class ito, no? Ito yung pinaka-efficient. Solid dito, solid. Solid, solid, solid. Siyempre, hindi ka naman gagawa ng solid na, na steel. Ang mahal, di ba? Ang pinakamataas to. Ito, hollow ito. Hollow, hollow. Hindi hollow. This is wide flange. Okay, I section. Hindi ka naman gagawa ng circular na hollow na beam. Mahirap, mahal. So, ito yung kaya ito yung pinaka. So, ito yung shape factor niya. So, try to derive this. Baka bigay ko sa exam ito. Okay. Okay, limit the state of shear. Pagdating natin sa shear, doon na lang natin pag-usapan to class. Okay? So, I will be giving you some. Maiksi lang naman yung shear. Okay, so these are just the, anong tawag dito class? Itong mga ito, combined shear, bending, shear, lateral, these are what? Perry. Ano yung mga ito? Nakalimutan nyo na yung lecture natin. You call this, anybody?
Limit state.
Okay, limit state. They are the strength limit state. Okay? Ikaw lang ang magsasabi niyang class. Hindi mo kailangan i-check lahat yan. Pag may experience ka na, hindi na. Wala na yung local backlink dyan. Siyempre, kailangan meron ka munang experience bago mo sabihin yun. Hindi na kailangan local backlink dyan. Hindi na kailangan yung deflection check dyan. Ito, serviceability ito, strength, di ba? Isa lang ang serviceability, ito ng deflection. Lahat dito strength limit state. Okay, so thank you for listening.